Ángeles, please, your microphone.
Sí, gracias.
No, okay.
¿Pueden escucharme?
Sí.
Gracias. Buenos días a todos. Un gusto estar el día de hoy con ustedes. The title of my presentation is Digital Soil Morphometrics of Coarse Fragments and Horizon Delineation in Soil Profiles using Digital Photographs. The history of soil and the environment can be inferred from the soil profile morphology and further elucidated by soil horizon properties. For many years, some soil properties, such as horizon delineation and the percentages of coarse fragments, have been evaluated qualitatively or semi-quantitatively. Recently, modern technologies, including computing resources, digital cameras, proximal soil sensors, have been used to improve the quantification of soil profile properties and thus improve sustainable land management. The physical properties presented in this study are important because they allow the identification of classification primary and secondary qualifiers, such as leptic, skeletic, and the leptosol soils group. And currently, the determination of these properties is mainly qualitative. In this sense, the objective of this study was to develop a method allowing the identification of horizons and the quantification of coarse fragments of volcanic soil profiles using digital images. The study area corresponds to the state of Michoacán, Mexico. The state of Michoacán is located between two physiographic provinces, the Transmexican Neovolcanic Axis and the Sierra Madre del Sur. Images of a cambisol and an andosol were used to develop the method, and 18 soil profiles photographs captured by the authors and others from the Series 2 of the Soil Profile Database of the National Institute of Statistics and Geography were used to test its operation. Photographs of the soil profiles captured by the authors were taken by reducing the surface roughness with a brush and using direct sunlight to obtain good lighting. The photographs were captured by positioning the camera perpendicular to the face of the soil profile and focusing on the entire depth of the pit. The color of the soil profile photographs corresponds to the three-dimensional system RGB that represents color using the presence or absence of the colors red, green, and blue. To increase the color differences between the horizons of the soil profiles, a key means segmentation preprocessing was used in the original RGB images. CLAB and HSV color systems were used to extract the color characteristics of the images and perform more precise calculations. In the CLAB color system, L represents the brightness of the image. A and B provide a color information coordinates that indicate variation from green to red and from blue to yellow. And in the HSV color system, H is the tone, S or saturation refers to the amount of gray in the color, and B or value represents the brightness or intensity of the color. The unsupervised K-means classification method was used again to segment the CLAB and HSV color system images. The K-means algorithm works by grouping the pixels of the image defined by the numbers of horizons in the profile. An interface was generated to allow the selection of the color systems groupings that best delimit the horizons of the profiles. Functions were generated for the extraction, smoothing, and overexposure of the soil horizon limits in the images of the soil profiles. And the ImageJ software was used to determine the depth, distinctness, and topography of the horizons. The distinctness topography of the horizons were defined based on the proposed area percentage reference charts from the United States Department of Agriculture Field Book. The processing of the soil profile images to calculate the coarse fragments was performed, number one, in a supervised manner, previously highlighting the coarse fragments in the original RGB image, and number two, in an unsupervised manner using the original image in RGB and the saturation component S of the HSB color system. To eliminate the texture of the images and to highlight the differences between in color of the objects, a grouping was performed based on the color entities using a superpixel function. Histograms were used to plot the gray intensity distribution and to identify the objects in the images. The histogram was used for the identification of the gray value that best represent the coarse fragments in the images. A binary image of the regions corresponding to the objects classified as coarse fragments was created. Empty space of the objects were filled, and a discrimination function for the roots based on the roundness of the object was created. The coarse fragments in the profile images was calculated in terms of the area percentage of objects classified as coarse fragments. For the evaluation of precision, the calculation of the absolute error, relative error, mean absolute error, and root mean square error was performed. About the results, the identification of depth, distinctness, and topography of soil horizons, the HSB color system performed better for the Cambisol and the C-Lab system for Andosol. The method testing using 18 soil profiles in general identify fewer horizons than in the field. The master horizons were mainly identified with both color systems, except for the Cambisol 3 and Cambisol 4, because their A and B horizons are morphologically homogeneous in color, but contain different amounts of coarse fragments. Horizons were identified for most of the soil profiles. However, the depths were different from those delimited in the field. About the rock fragment percentage for Cambisol, a better result was obtained with the image of the S component of the HSB color system. For the andosol, the differences between the soil components were more evident in the original RGB image. In an unsupervised processing, several coarse fragments edge blended into the soil matrix due to the adhering of fine earths. So the coarse fragments were underestimated, making the unsupervised processing method the poorest estimator. About the method test, supervised processing produced the best test results. For the endosols in the test, supervised processing with the RGB images was the best option, and unsupervised RGB processing performed better than the S component for cambisols. We created a graphic system for decision-making to delimitation of soil horizons and quantification of coarse fragments in digital images of soil profiles. To delimit the horizons, we recommend determining if their colors are contrasting and if the image contains raw, shiny, or shadow areas. And additionally, the source of the image should be considered, as the application of the method is different if captured the images for processing or collected from legacy data resource. For the quantification of coarse fragments, we advise using a brush and, if it's necessary, a razor to clean the profile face, the roots, and remove the fine air stuck to the coarse fragments before taking the picture. Given the edaphic variability that exists, more photographs of soil profiles should be studied that include low, medium, and high color contrast between soil horizons. Profiles with concretion should be included too, and other soil reference groups, such as the non-percolating calcisols, gypsisols, solonchaks, and solonets. Well, the study area contains soil profiles with high and low contrast colors in their horizons and coarse fragments, even in soils of the same reference group. Therefore, we recommend adapting the application of the digital photograph analysis method to the particularities of the soil profile. The results of this work allow a better selection of methods for processing digital images of soil profiles and for transitioning from visual estimates by experts to digital quantification of soil properties. Regarding soil classification, the methods presented in this study could be used for the identification of the rhodic, chromic, leptic, hyperskeletic, and skeletic qualifiers, and the leptosols group with a digital approach. And
Okay, yeah. Questions for Ángeles? Yuri?
Yes. So I find very interesting your presentation, your study. Thanks for sharing it. So what kind of sensor, I mean, what kind of camera have you used it? And what was the format of the file? Was it like a JPEG or RAW?
sí, bueno, sobre la cámara utilizada fue una cámara Canon PowerShot. Es una cámara de gama media, incluso los celulares que se utilizan, los más modernos, como los iPhone o los Samsung de nuevas generaciones, toman mejores fotografías que esta cámara que utilizamos en campo. Y sobre la segunda pregunta...
Stop.
We are
need to
making the
translate,
translation.
perdón.
The camera that she used was a Canon PowerShot. It was a medium standard camera because nowadays the cell phones like iPhones or that high they have the high resolution. Yeah.
Y la segunda pregunta, ¿cómo alcanzas a
Can you repeat the second question?
Yeah,
please?
Type of el tipo de archivo.
The type of file, did you use RAW?
Sí, utilizamos el archivo JPG que obtuvimos de la cámara. Por eso es que está en el sistema de color RGB. Y después realizamos la conversión a los sistemas CLAB y HSV para hacer el procesamiento.
She used the JPG format, so that's why they use the RGB scale color, and then they process to the other formats. Could you repeat the formats, please?
CLAB y HSV.
Gracias.
Gracias. Thank you.
Please. No.
First, okay. Thank you very much, Ángeles. Your work is very nice. I have a question concerning the quantification of rock fragments, because in some soils we can soils with calcium carbonate concretions. Maybe we will have the same approach and then we miss some information, or we fail in the identification of these kind of things. How to improve the identification?
Sí, con respecto a eso, por eso propusimos el procesamiento de las imágenes de dos formas. Primero, de forma no supervisada, utilizando las imágenes tal cual vienen de los dispositivos RAW crudas. Y otra forma de procesamiento fue la supervisada. Entonces,
Just stop.
Stop, please.
They use the original files to make the first approximation or the first studies.
And then?
¿Puedes continuar, por favor?
Sí. La segunda forma de procesamiento que propusimos, perdón, es que con eco. Ya, gracias. La segunda forma de procesamiento de las imágenes fue con procesamiento supervisado. En este procesamiento realizamos, digamos que resaltamos previamente los fragmentos de roca en las imágenes y después ejecutamos el algoritmo para hacer la cuantificación. Entonces, para este tipo de suelos, si en campo sabemos que esos efectivamente son concreciones y no fragmentos de roca, cuando hagamos el procesamiento podemos identificar únicamente los fragmentos de roca de forma supervisada.
So they use for the second process of identification the material that they in the field. If they look that they were fragments of rocks, they identify them by the second process with the algorithm, or they could remember if they were rocks or they were these calcium.
Thank you.
Thank you. Martin?
My question is connected with this, that did you check these results that you have with the amounts that was measured by other methods? So we saw some results on this presentation, but we are not sure are they the same like we, for example, can obtain from the fieldworks. So did you check your results? Did you validate it somehow with the other type of data, like for example estimating of the coarse fragments in the field or something like this?
Ok, si entendí bien la pregunta es si comparamos las estimaciones visuales con las realizadas con el procesamiento. ¿Sí la?
Sí.
Estas fórmulas que utilizamos del error cuadrático medio, el error absoluto, lo que hicimos fue precisamente comparar los cálculos realizados con el procesamiento supervisado con las estimaciones visuales. Entonces, cuando hicimos estos cálculos,
they compare the processing with the error estimated, the estimated error, the mean error, the standard error, and with the estimations that they were using.
Yes. first estimate.
Comparamos las estimaciones visuales con las cuantificaciones con el procesamiento supervisado. Y ahí pudimos ver como qué tanto error tenían tanto las estimaciones visuales como el procesamiento no supervisado. Digamos que tomamos como el valor verdadero, el valor correcto, el que obtuvimos del procesamiento supervisado.
And they compare the supervised values with the observable, with the estimated values.
So they evaluate both. First, the image, and this was without control. But later, they estimate with a supervised model. In this way, they could estimate the error of the method and then to do a better approach. I think this is okay?
That's great, thank you.
Last question.
Sorry, a very critical question. You did a very nice approaches, and we saw how you can shift the picture to different with different information. Now, I tried earlier, very simple, but I came to the conclusion that a picture alone is not able to give enough information on a soil, because if you make a picture of an undersoil and if you don't know it is an undersoil, it doesn't help, and the cambisol is the same. So you must have more information than a picture in order to know which soil you have.
Sí, estoy de acuerdo. Por eso en las conclusiones mencionaba algunos calificadores primarios y secundarios particulares a los cuales se les pueden asociar los criterios de diagnóstico con estas propiedades que trabajamos. Efectivamente, con estas propiedades no podríamos, por ejemplo, clasificar andosols, pero sí los leptosols, porque precisamente las dos propiedades que nos permiten clasificarlos son su profundidad y el contenido de fragmentos gruesos o de tierra fina que sea menor a 20%. Es por esto que solo mencionamos esos. Ay, perdón.
Basically, she agreed, and this method is not applied for all soils,
Yes.
but it works very nicely with leptosols, because these soils are not so deep, they have a lot of rock fragments, but with other soils, for instance, andosols.
Yeah, but I even do not agree with leptosols, because the properties of the stones you don't see in the picture.
Yeah.
Sorry.
Well, thank you,
Gracias.
Ángeles.
Thank you.
Congratulations. Coffee break.
How long?